that picking up my voice? I hope so. All right. So, we've got an ion which has got no charge, going to give ion 2 plus. So what is happening, it's losing those electrons. Yeah? Where are those electrons going?
To oxygen.
To oxygen. So how do I write that as an equation? I've got oxygen. Well, oxygen is going to give what? 2 lots of O2 minus. Yeah, 2 lots of O2 minus. How many electrons does that need? 2 lots of 2 minus is 4 electrons. Yeah? So what I should do, make a bit more room, plus 4 electrons. Our iron's only given me 2, so I need 2 of them, which actually matches our equation.
You need to change the electron and the Fe, the ion reaction.
Thanks. Done. Okay. So if this is oxidation, what is this? Reduction. So those together make up a redox reaction. Yeah? Yes? You can't have reduction without oxidation. You can't have oxidation without reduction. Yeah?
So how did you get oxygen plus 4 electrons?
Okay, because I've gone from oxygen to oxide ions. And an oxide ion has got a -2 charge, which means it's grabbed 2 electrons to get its full outer shell. So I need 4 electrons because I've got 2 lots of 2 minus.
But it's no longer O2.
No, it's just single oxide atoms,
Oh.
or ions.
Okay.
Yeah? So I need 4 electrons for that to happen.
Yeah.
Yeah? Did you do earlier balancing some redox equations? What do I call this? Just one bit of it. It's a half equation. Okay, so I've got an oxidation half equation and I've got a reduction half equation. Have you gone through how to remember what's oxidation, what's reduction?
Yeah.
What? Oil rig. Oxidation is loss, reduction is gain?
Yeah.
Yes? All good. Okay, let's do a really small prac. Beaker. Okay, so here we go. Let's see if I can get this. Copper sulfate. This is pretty concentrated copper sulfate. It is a beautiful colour. I've got some zinc. All right, I've got some zinc. When I pop the zinc into the copper sulfate, okay, so that's been what? Less than 10 seconds?
Is that blue?
Okay. No, it looks black, but it's got a bit of a coppery sort of a look. I'm just going to leave it on there for a little bit longer. It really does not take very long. You start seeing a bit of a coppery colour there. So guess what is that? What's that? It's copper. It is actual copper. Okay, so let's have a look at what's happening here. So I've got copper sulfate. Copper sulfate, because it is dissolved, is in the form of copper ions and sulfate ions. Yep, it's dissociated completely. I pop in a bit of zinc. Yeah? What formed on the outside of the zinc? Copper. So I've gone from copper 2 plus to copper. Yeah? What's happened to it? Okay, so I've gone from copper ions, and the copper ions are blue. That's what actually gives it its blue colour. Okay, it is blue because of copper ions floating around. It has gone to straight copper. So in this case, I could actually put, this is aqueous, and it's turned into copper solid. And what's happened to what's happened to the copper ions? They've gained 2 electrons. Okay, so in other words, the copper ions have been, what's the word? No, they've gained electrons. What do we call a gain of electrons? Good. Have been reduced. They have been reduced. The copper ions have been reduced. You cannot have reduction without oxidation. So what's been oxidised? The zinc. Okay, so that's pretty much the only other thing that we've got in there. So the zinc has gone to give what? Zn2 plus. Let's write a 2 that's legible. Plus 2 electrons. Okay. All right. Let's pop some states in here. What state is my zinc in? What state is my zinc? What are my zinc ions? Aqueous. Okay. Plus my electrons. So what has been oxidised?
Do electrons have states?
No. We'll come to that in a second. It's like a direct transfer, but I'll draw that in a diagram. Okay, so what can I've written a sentence here. Copper ions have been reduced. What's happened here? Another sentence. Zinc has been oxidized. Is it ions? Is it atoms? What is it? Atoms. Zinc atoms have been oxidized. Okay, once again, you can't have reduction without oxidation. Now, let's put some new terms. The copper ions have been reduced. What were they reduced by? They were reduced by the zinc. Okay? So the copper ions were reduced by the zinc. So we can say that the zinc, let's do a different colour. The zinc is a reducing agent. Does that make sense? Yeah. It's a reducing agent because it has reduced, in other words, it's provide electrons to, the copper. Yeah? So the zinc itself is oxidised, which means it's a reducing agent. Yeah? So what can I say about the copper? And what I need to be really careful about what I say here. What is copper ions? If I said copper, I'd be wrong. Because it's the copper ions that are acting as an oxidising agent. Okay? The copper ions are an oxidising agent. Yes? So, reducing agent, oxidising agent. There's another word for those. Does anybody know what they are? An oxidising agent is also called an oxidant. A reducing agent is also called a reductant. So all terms, they're all related, and it's sort of backwards. The copper ions are reduced, therefore they're an oxidising agent. The zinc is oxidised, therefore it is a reducing agent or reductant. So the terms are fairly interchangeable. I'm not sure, yeah. I'm not sure it's actually picking up much. There we go, doesn't matter. All right, yes, no? What's going to happen? Here we go, let's have a look at this. Whoa, it's just fallen off.
Oh.
Yeah, let's try and scoot this on here. Yeah. What have I got? It's copper. Okay. Right, and it's just sloughing off the outside. It's just coming straight off the outside. Okay. That's copper. sort of is if you talk about ions changing into atoms and atoms turning into ions. So, what did you just say in terms of what's going to happen to the zinc?
It's decaying.
Not decaying. Well, realistic.
I know it's not decaying, but
Yeah. Okay. It's turning from a solid into an aqueous solution. So what's actually happening to the piece of zinc? It's dissolving. It's literally going to dissolve into the solution. So if I left this overnight, what's going to happen to the colour, first off? It's going to go less blue. I can say it's going to become colourless. I can't, is that clear now?
No.
It is clear. I can see through it. That means it's clear. But is it colourless? No, it's blue coloured. So if there has been an HSC question in regard to explaining what happens in this, or something very similar. So the blue colour will lessen, it'll get less blue, or it will eventually become colourless. What's going to happen to the piece of zinc? It's going to dissolve, okay, because it's going to be turning into zinc ions. Yes.
Could you say that the zinc is dissolving and displacing the copper?
And that's the next word we're going to look at, because this is called the displacement reaction. Okay?
Would the copper just be like a sediment at the bottom?
Yeah, and it's exactly what is happening. Okay? Now, let's kill this. This is an example of a displacement reaction. There's a whole heap of things a couple of things we can say. This is a redox reaction. It's also called a displacement reaction. Okay? The zinc ions are displacing the copper ions from a solution. Yeah? Does that make sense? The zinc ions are taking the place of the copper ions. Alright. Let's mop up my mess. Can I get you to open up the front of your books? Okay, the front of your book, so you've got your periodic table. Let's turn this on. I need to use my laptop. Yes.
We should record every lesson.
Oh, it's going to be painful. I need to get an extension for my speaker, I think. You're not going to watch them. It'd be so boring. What am I doing? Could. You could.
Or you could just come ask you.
Just ask me. What are we doing? I'm going to Year 12. Where's my files? Board of Studies. I need the data sheet. I just need to go and get another dongle, girls, sorry. All got your data sheet in front of you? I want it on the other side to the periodic table. Maggie, you're awake? check the input terminal. Okay, guys, this is called the table of standard reduction potentials. So if I just zoom out so you can actually see it a bit better, let's close that. Okay, so this is on your sheet. You should have it in the front of your booklet. Okay, now this shows effectively how likely it is that something will be reduced. Everything's written as a reduction. Everything, like potassium has potassium ions have got an electron added, etc. All the way, they are all written as reductions, but they can be swapped, which we'll go into in a second. So, what this is useful is if I get, say for example, let's go some zinc sulfate. I've got some zinc sulfate solution, and I pop a piece of silver, not a bar of silver, into some zinc sulfate. Is a reaction going to happen? Now, that one that I used, here we go, a reaction happening easily. We can see it immediately. Is a reaction going to occur if I pop a bit of silver into some zinc sulfate? And that's what we can use this table to work out. Okay? Now, these numbers range from a negative number all the way down to positive 2.89. Okay? This just means fluorine is likely to be reduced. And if we go back up here, potassium is very unlikely to be reduced.
Can I ask a bit of a stupid question? Why is it at the bottom they have half?
Okay, we're just talking about half a moles. They've just balanced it so it's only effectively they haven't even done that. You could write it as just fluorine plus 2 electrons going to 2F minus. I don't know why they've done that specifically. For example, I've got 5 electrons here. It's just the way they've written.
That side just one.
It looks like,
To make like a ratio.
and that's what it is. That's what it looks like. So, where is silver? Silver here is 0.8. Okay? So that's pretty likely to be reduced. Okay? If I go up to zinc, zinc is minus 0.76, which means it's very unlikely to be reduced.
How can something be minus? Yeah.
We're going to come to, because we'll look at this in terms of when we look at what's called the standard cell, standard hydrogen cell. But we'll be using these numbers later. At the moment, all that we're going to be looking at them is, the more positive the number, the more likely it is to be reduced. Okay? So in this case, silver is much more likely to be reduced. Can I get them both on the same screen? Yep. Silver is much more likely to be reduced. So there's silver than zinc. So, tell me something about that silver.
It's more likely to swap.
It's more likely to be reduced. Can that be reduced? What type, this is silver. Not silver ions, it's just straight silver. That means it's already got, it's got all of its electrons. Yeah? Well, it's already got all of its electrons, it's not going to grab any more. Therefore, for this one, I'm going to have no reaction. Does that make sense? Okay, let's look at another example. This one obviously is going to have, where's the eraser? Give me some solutions, or give me some reactants that there's not going to be that there will be a reaction.
It will be.
I want you to tell me something that will form a reaction. Will have a reaction. Any ideas?
Like solid calcium.
Okay. Yes, well, I could get solid calcium. All right. So I'm going to put. I've never seen a bar of calcium this big. I've seen small little chunks, but here we go. I've got a bar of calcium, and what am I whacking it in?
Iron.
Let's go iron 2 nitrate. Okay. Will there be a reaction?
Yes.
Why?
Because it's solid calcium.
Now, have I got iron 2 there? Yeah, iron 2's there.
Yeah.
All right.
Because calcium
Calcium's negative.
has
So, calcium's up here.
Negative 2.8.
Iron 2 plus is here. And you really do need to be careful because there's also an iron 3 plus lower down. So you need to make sure you find the right one. And I've got iron 2 plus.
Is it more likely that there will be a reaction if the difference in the numbers?
The bigger the numbers, any difference in numbers is going to be a reaction. Okay? But we'll talk about that. This is leading on to batteries. It actually leads into batteries.
So if there is a reaction, the bar
Yep.
would be negative because would that mean
Okay.
it will oxidize?
Just the fact that this one is more likely to be reduced than this one.
Yeah.
Do I have ions in here?
Yeah.
Yes. So it's likely that this reaction will occur. So what I want you to do is, I want you to write the half equations for this. Do you want me to help you with this one?
Yes.
Yes? Then,
So if there's any difference,
yep.
there'll be
There could be a reaction, depends on which one's ions and which one's not.
so lower down it has the chlorine and
Yep.
Cr,
Chromium?
chromium oxide,
Yeah.
that they have the same voltage.
Okay, in which case if you had those two together, there's not going to be a reaction. No reaction whatsoever. Okay. What are these? This is a half reaction. Yeah? This one is more positive. This one is more positive. I've got ions in here. So this reaction is just going to happen as written. Fe 2 plus 2 electrons is going to go give Fe. Okay? What do I call this? This is called reduction. Okay? Reduction. What's being oxidised? You can't have one without the other. If that's being reduced, what is being oxidised? The calcium. This equation is written as a reduction. See, it's got a double-headed arrow. That means it can be written either way. So what would be my oxidation half equation? You just swap around. So I've got calcium going to give calcium 2 plus 2 electrons. Yep. And this is my oxidation. I would lose a mark if I did this in the HSC. What have I left out? States. Okay, so, and I know that this doesn't have the aqueous. I still want you to put aqueous in. That's aqueous. That is solid. That is solid. That is aqueous.
What if you had iron 3 plus with calcium 2 plus?
Okay. Is going to... Then we've got something a little different. I wanted to approach that later because iron 3 plus and iron 2 plus are actually a different issue. Okay, I'm going to talk about that later. Okay, yep.
So basically with these ones,
Yep.
the aqueous one has to be
Lower down. Yep. That's pretty much what it is. If you're talking about a direct reaction like this. All right. Now, I'm going to give you some to practice and you can work out and write down the half equations. Why is that not muted? was that?